or journal, Theoretical and Applied Mechanics Letters, abbreviated as TAML. It's my honor to start this webinar. Before we delve into today's stimulating discussions, please allow me a moment to introduce both our journal and today's webinar. TAML aims to publish cutting-edge research in theoretical, computational, and experimental mechanics, emphasizing originality and rapid dissemination of advances in science, engineering, and technology. Our impact factor for this year stands at 3.2 with a CITE score of 6.2, reflecting the high quality and relevance of our published research. We ensure swift publication with the average time to first decision of just 3 weeks, facilitating timely exposure of groundbreaking work to the academic community. TAML is led by Editors-in-Chief Professor Guowei He and Professor Yonggang Wang. Our dedicated team consists of 75 editors and board members from 17 countries, all affiliated with prestigious universities and research institutions. We are committed to provide exceptional support to our reviewers, authors, and broad community, guiding you through every step of the publication process with our extensive expertise. We warmly invite you to consider submitting your research to TAML and join our growing community of contributors. Let's move on to next slides to introduce the specifics of today's webinar section. This webinar is jointly hosted by TAML, Elsevier, and Chinese Society of Theoretical and Applied Mechanics at the National Nature Science Foundation of China Basic Science Center program, focusing on multi-scale problems in nonlinear mechanics. Our goal is to offer an international platform for researchers to communicate and share their latest work, fostering, collaborating, and advancing knowledge of our field. You can follow the webinar through our webpage on Elsevier and CSTM, join our WeChat group via the provided barcode, or follow us through our other communication channels for continuous updates. Finally, I would like to extend our heartfelt gratitude to everyone involved in making this webinar possible. Special thanks go to today's speaker, Professor Pen Chen, and today's webinar host, Professor Lianping Wang. Your contributions are invaluable to the success of this event. Thank you for your attention, and I will look forward to an engaging and informative webinar. Now, I would like to pass the baton to our webinar host, Professor Lianping Wang, who will take us through the next section of our webinar. Professor Wang, over to you.
Thank you. Good morning. Welcome to TAML seminar. I'm Lianping Wang from Southern University of Science and Technology. It's a great honor for me to introduce Professor Cheng Peng today. He obtained his bachelor degree from Xi'an Jiaotong University in thermal energy engineering, and then went to the graduate school at Chinese Academy of Science to obtain a master's degree. And then he came to University of Delaware to work with me for PhD degree. He obtained his PhD degree in 2018. Then he went on to Penn State, did a postdoc, 2 years, spent 2 years there. Then he was invited to join Shandong University as professor in mechanical engineering. Dr. Peng researches in multi-phase flow area, in particular particle-laden turbulent flow. He developed a fully resolved simulation methods based on lattice-Boltzmann method, and then applied them to study interaction of between turbulent flow and finite size particles. So far, he has published over 40 journal papers in prestigious journals such as GFM, GCP, and Physical Review E, and so on. So as many of you know that in multi-phase flow, in the last, at least during my career, in the last 40 years or so, there was a quite rapid development in simulation methods, starting from point particle, and then later on evolved to interface or particle resolve, interface resolve simulation. And so it's very exciting to hear Dr. Penson's talk today titled "The Study of Particle-Turbulence Interaction Using Fully Resolved Simulations Based on the Lattice-Boson Method, Review and Recent Progress." So now I pass on to Dr. Peng, please.
Let me first turn on my mic. Okay. So thanks for the introduction from my own PhD advisor. Good morning, everyone. My name is Chen Peng from Shandong University. Today, I will give a talk on the study of particle turbulence interaction using fully resolved simulations based on the Lattice-Boson method. I will give a review on the method itself and introduce some of our recent progress. So my talk will contain these 5 aspects. First, I will give a background. What is the particle-laden turbulent flow? And what is the particle resolved DNS or fully resolved DNS? Then I will give a brief introduction of the method, which is the Lattice-Boson method. And I will give emphasis on the boundary treatment. There are 2 very commonly used boundary treatment on the particle surface, which is the bounce back rules and the immerse boundary method. And then I will show you some recent progress of how we apply this method to study the particle-laden turbulent flow. And finally, I will give some conclusions and take-home messages. So what are particle-laden turbulent flows? And the particle-laden turbulent flows are multi-phase flow, consist of a continuous phase, which is usually fluid, and a dispersed phase, could be particles or droplet or bubbles, if the droplet and bubbles are sufficient small and cannot deform. And it can be found in many natural phenomena such as sandstorm, like volcano eruption, and the sediment transport in the riverbed, and also in many engineering applications. For example, in this animation, I show the fluidized bed and continue a lot of particles. So that's I give a basic definition of the particle-laden flow. And why we want to study the particle-laden flow, and what are the essential questions we want to answer. So there are 2 essential questions. The first is how does turbulence affect the particle motion? For example, if you see this movie on the left, this is a particle moving in the cyclone. And if we want to know where the particle will go, then we need to know the force acting on this particle in the turbulent environment. And this is usually coming from the equation of particle motion. But for the more general scenarios, like how we should refine this equation of motion, is still a quite open question to answer. And also, we're also interested in how the turbulence affected the group effect of particles. For example, the collision rate, and also the preferential concentration. And this is a quite important topic for some applications like chemical engineering. And also, we also want to know how particles modify the turbulent flow, the property. For example, in this figure, you see a fireman holding a water hose, right? So the pressure difference between the inlet and outlet of this water hose is fixed usually. So if we can reduce the stress, the wall stress in this hose, the water can go further, and I mean, in this case, can save more lives. It's quite well known that if we add some particles, of course, it's not a spherical particle, it's usually some long fibers, we can greatly reduce the wall stress. And this is another thing we want to know, like how do particles modify turbulent flows? And unfortunately, in many applications, these two questions are coupled together, meaning if the turbulence is modified by the particles, it will have a feedback effect on the particle motion. So these two questions are usually coupled, which make the particle-laden turbulent flows study quite complicated. And so how do we like study this complex particle-laden turbulent flow? And of course, back to 1980s, like many scholars had done quite some beautiful theoretical work. But nowadays, I think the particle-laden turbulent flow are too complicated to do pure theoretical analysis. So normally, as other fluid dynamics problems, we can do it. We can start it with experiments or the simulations. Of course, you can always argue about the advantages and disadvantages of these two methods. For experiments, if you do it carefully, I mean, it's physically reliable. At least most people will believe so. And it can apply to realistic physical conditions, meaning you can have a quite complex geometry. But it's also relatively expensive to conduct. For particle-laden turbulent flow nowadays, the most commonly used experiment setup is the PIV. But now I think the great resolution, the resolution of the PIV system is a little bit tricky to resolve the disturbed flow around the particles. And also it's kind of restricted to realistic condition. For example, if you want to study like the particle following with a certain density ratio, it's yeah. So then like it's a little bit tricky to find the real, like say, particle and fluid in the real world. But in the numerical simulations, that's kind of easy to do. You just change a parameter, right? And you can do whatever like the whatever parameters, density ratio and viscosity ratio you want. But there are also some disadvantages for numerical simulations. For example, it's nowadays still like although we have done many studies, but most of them are limited to idealized conditions. For example, homogeneous isentropic turbulence, wall like a channel flow or pipe flow. It still is very difficult to do like realistic problems. And I think one of the biggest advantages of doing numerical simulations compared to experiments is like we can actually resolve everything around the particle if the gray resolution is sufficient. Then it gives us a lot of information to modeling the problem and to review the mechanisms. So if we choose to do our problems with numerical methods, what numerical method should we use? It depends on the problem. I mean, one principle is that there is no universally good numerical method. The good numerical method depend on the problem you are targeting at. So there are basically three parameters, non-dimensional parameters that would determine what numerical method you use. The first one is this is volume fraction. And the second one is the Stokes number, which determines the inertia of the particle, like how tightly a particle follow the fluid motion. And the third one is the particle size. So if the particle inertia and particle size are both small, particle will follow the fluid tightly. So you don't have to track the particle motion. You can get the particle velocity from the fluid information. But if the particle inertia become larger, it will no longer follow the fluid tightly. Then you need to solve the particle motion separately. And there are two methods. The first is if you are treating with dense particle motion, then you can assume the particle phase as another fluid phase and solve the Navier-Stokes equation. This method is the two fluid method. But I think this method lack of the solid background because physically it's very difficult to develop like a Lagrangian, like Eulerian description of the particle motion. I mean, so if the particle inertia is even farther, or like if the particle phase is not dense enough, then a better way is to track the particle motion by solving the Newtonian equation. This method is called the Lagrangian method, and there are two types. If the particle is not large enough, meaning the size is relatively small compared to the Kolmogorov length, then you can treat it as at a point mass and use the point particle method. But if the particle size is large enough, is larger than the or comparable to the Kolmogorov length, then you have to apply the fully resolved method. I put a caution mark here is that if you want to extend this figure to the LES, then you have to be careful because this is from our DNS results, is that although the particle size is much smaller than the large size of the vortices, it will have some effect on the large scales. And you notice that in the LES, this scale, this eta here is the subgrid scale. It's not a physical scale, but a numerical scale. So if you want to apply this figure to LES, I would recommend you to use it with caution. Okay, but this is just my point of view. So again, we emphasize that the choice of the simulation methods depend on the specific problems. And so why do we use the fully resolved DNS? There are two reasons. One is that, as I mentioned before, if you do like Lagrangian particle tracking, you usually like solve the particle motion using this equation for motion. This is the famous, as a Chinese, I should call it a TAI, Maxi-Rayleigh-Gordino equation, because this was first derived by a Chinese scholar, Cai Shu Tang, back to 1950s. But this equation only apply rigorously to when the Reynolds number is infinitely small. So for the finite Reynolds number case, how should we refine it? And the information could come from our fully resolved DNS. The other thing is that because a lot of particles like effect on the turbulence actually happened on the disturbed flow around the particle. So it's critical to resolve the disturbance flow around the particle. I show some figures here. For example, it is well known that the particles will enhance the dissipation rate of the turbulent kinetic energy in turbulence. And it can be directly seen from our fully resolved DNS that the dissipation rate around the particles has been enhanced. So in many cases, if we want to understand better the interaction between the fluid and the turbulence, the fully resolved DNS is the only way out. So if we choose to do fully resolved DNS, so what methods are available for us to use? I characterize these methods into two groups. The first is called body-fitted methods, basically solving the Navier-Stokes equation in a time-dependent domain subject to the change of particle motion. And the advantage of these methods is, of course, it's very accurate and it's easy to satisfy the node supercondition because you have the grid nodes precisely on the particle surface. But the disadvantage is that if you apply this method to moving particle problem, once the particle move like quite some distance from its original problem, then you need to remesh. And this remeshing could be very expensive. Of course, examples of these body fitting methods include the arbitrary Lagrangian Eulerian method and the overset meshes, and they have been applied to particle-laden turbulent flow simulations, but with a small number of particles with a described motion. And another set is called the Eulerian method. Basically, only use a fixed Eulerian grid to solve the flow. And these methods are relatively simple to realize because you don't have to remesh. But the disadvantage is that since you don't have the grid node on the particle surface, you will need some techniques to implement the no-slip boundary on the particle surface. In fact, this is a bottleneck of the particle-laden turbulent flow simulations. And there are also quite some mature mature methods. The most commonly used immersive boundary method. A lot of you have already know this. It's basically change the no-slip boundary enforcement to a current force. And the DFD method developed by the Professor Yu Zhao Shen's group at the Zhejiang University. This method basically used a force field within the particle to enforce the rigid body motion. And the Physalis method, this is a very special method, which basically assumes the flow around the particle satisfies Stokes solution, like in the particle reference, because due to the no-slip boundary condition, the flow around the particle has velocity very close to the particle surface. So you can use a Stokes solution and you can map the coefficient. You can solve the coefficient in the Stokes solution by mapping the solution out in the out region. And the last one is the lattice-Boltzmann method. Of course, it's not a very good appropriate to like place the lattice-Boltzmann method here, because I think lattice-Boltzmann method is more of a flow solver, like finite difference, finite volume. But there are some review papers that they treat they like classify lattice-Boltzmann method as a boundary treat technique. So then I will give a brief introduction of the lattice-Boltzmann method, why we use this, and why do we think it's a very good method to solve particle-laden turbulent flow problems. The lattice-Boltzmann method solves the lattice-Boltzmann equation, which can be viewed as an indirect way of solving the incompressible Navier-Stokes equations. So at the first glance, this equation does not look like a Navier-Stokes equation at all. So many people in doing conventional CFD simulations will criticize the lattice-Boltzmann method, saying, "Oh, you are not solving the Navier-Stokes." But we can rigorously show that from Taylor expansion and, of course, using the technique called Maxwellian iteration, the distribution function of the lattice-Boltzmann method will look like this. It contains a lot of this component, and many of that you will know that every like ingredients in the Navier-Stokes equation, for example, the unsteady term, the pressure gradient, this nonlinear advection, and the diffusion terms are all contained in the lattice-Boltzmann, in the expansion of F. So by taking the moments, taking moments meaning like we sum up this F multiplied by the constant discrete velocity E to some extent, typically the zeros and first order moments, we can see that we get directly the continuity equation and the momentum equation. If we make the equivalence between these moments of F and the hydrodynamic quantities in the Navier-Stokes equation, then we basically recover rigorously the Navier-Stokes equation. So solving the LBE is equivalent to solve the incompressible Navier-Stokes equation. This has been proved by many people with many different methods. So why do we think LBM is suitable for fully resolved DNS for particle-laden turbulent flow simulations? Of course, comparing to the conventional Navier-Stokes solver, for example, finite difference, finite volumes, LBM has some advantages and disadvantages. It is a quasi-linear equations, which is easy to solve. In fact, the beautiful things about LBM is that the local operation is nonlinear, or the nonlinear operation is local, and all the non-local operations are linear. So this feature makes LBM quite easy to implement. It's also very flexible in model design and boundary treatment, because the variables you solve is the number of variables you solve is larger than the conventional CFD, which is basically the velocity and the pressure. And also it can avoid solving the pressure Poisson equation, and it's intrinsic second order accurate. And the numerical diffusion is very small in the Lens-Bolton method, because the advection in the LBE is a Lagrangian treatment instead of Eulerian treatment. Of course, this also gives the LBM some disadvantages. For example, its computational cost is usually higher. You need more memories to store these more variables. Of course, this disadvantage can be partially solved by using some techniques. For example, the lattice kinetic scheme. Also, it's restricted to isotropic and homogeneous mesh. But this problem, the second disadvantage, is no longer a problem, because if you have particles, particles will create some local high dissipation rate, dissipative regions, and you need a larger resolution to resolve. So if you look at the conventional CFD method, for example, immerse boundary, when they apply to particle-laden turbulent flow simulations, they are also not using this non-uniform mesh. They're also using this isotropic uniform mesh. So this constraint of Lens-Bolton method is no longer a problem. And also some people criticize LBM, said, okay, you only have second order accuracy. You cannot go for higher order accuracy. But this is also not a problem, because in these particle-laden turbulent flow simulations, the bottleneck is how you treat the particle no slip condition. And many of the famous methods, for example, the immerse boundary is only first order accuracy. So second order accuracy is no longer a problem. And also the LBM, because it has a very small numerical diffusion, it will have some worse numerical stability. But this can be also solved by using more stable LBM, such as a cumulant LBM. So by this argument, we think LBM is suitable for fully resolved DNS for particle-laden turbulent flows. Of course, we want to emphasize again that we're not saying LBM is a universally good method. It depends on the problem you're targeting at. So in this figure, in this slide, we compare our, for them, the left panel, we compare our LBM algorithms. We try to see what the scalability in the parallel computing. And as you can see, with some good data communication strategies, both our single phase and particle-laden codes can have almost idealized scaling speed up. And we also compare the computational speed of our method to some other methods. For example, this final volume immerse boundary method developed by our colleagues in Europe. And I think their code is one of the best in the world. And our computational efficiency is comparable. I mean, at least it's a little bit slower than their method, but not too bad. And I think this largely because we are not good at like improving the computational efficiency of our code. If we can optimize our computational efficiency, it would be, this comparison would look better. And the history of the using LBM for particle-laden turbulent flows, particle-laden flow studies can be traced back to 1990s. The pioneer researchers, Tony Ladd and Aiden, they they conduct some direct numerical simulation of particles for particle suspensions, but back to their area, they're mostly limited to laminar flows. And starting from 2000s, Dirksen mostly and his collaborators started to use the combined LBM with Boltzmann, the Boltzmann with immersed boundary to study particle-laden turbulence studies. This shows this is the very first particle-laden turbulent fully resolved simulation done by Tenkate, basically Dirksen and his collaborator. And after 2011, Gao, basically from Professor Wang's group, present the first, I think, the interpret bounce-back based particle-laden turbulent simulation. And then there are more people's. One of the very amazing simulation was done by Gear in 2017. And as you can see, they can apply a direct numerical simulation based on the Boltzmann method to study the drag crisis of particles for extremely high Reynolds number. I doubt if this can be done by other conventional method. If you can, you may challenge yourself to do this. And also the immersed boundary based LBM, also many people have applied this method to turbulent particle-laden flow. So I want to emphasize one of the key features of the LBM, which is the flexibility in boundary treatment. So how do we treat the no-slip boundary? Because this is a bottleneck for particle-laden turbulent flow fully resolved simulations. And there are mostly two categories. The first is called the interpret bounce back. Basically, it's like you use the known distribution function and the hydrodynamic constraints on the boundary to directly construct the unknown distribution functions. And a very good example of this is the single point second order bounce back scheme, which only requires the local information. You don't need to do special interpolation, which in parallel computing is save the computational, it will save the computational speed by cutting off the data communication. And once you have this unknown distribution function constructed, the no-slip boundary is implemented, and the force and torque acting on this solid object, for example, particle, can be computed by this momentum exchange method. This combination of interpret bounce back plus the momentum exchange method can always ensure the second order accuracy. So it preserves the order of accuracy of the flow solver. And I think another good advantage of this is it is very convenient to analyze, because you have the expression a few slides ago, you have the expression of F. So you can analyze everything. You can explicitly write out what's in this F and D, what you are calculating. Of course, the disadvantage is that using the bounce back, interpret bounce back, you need some skills to implement when the geometry is complex, because all these interpret bounce back, you need to calculate the relative distance between this boundary node and the solid wall. And this is not a very easy job to do if, say, your particle is a cylindrical moving particle and has a complex geometry. And because the diffusivity of this using this interpret bounce back is relatively low, then it's more vulnerable to acoustic noise. This is another issue which will give sometimes cause the numerical instability. Because when you use interpret bounce back, usually you don't have the fluid information inside the particle. So if the particle moves and it uncovers a new fluid node, then you have to initialize the distribution function on this newly uncovered fluid nodes. And here I give an example of our newly developed like a purely local construction on this node. And if this process usually we refer it as refilling, and if this refilling or the initialization of distribution functions on these new fluid nodes is done inappropriately, then it will give you this very severe acoustic noise, and it usually will kill the simulation, will make the simulation unstable. Another big category of boundary treatment, and many people use it with LBM to solve the particle-laden turbulent flow, is the immersed boundary method. And in the LBM world, the immersed boundary has nothing different to the immersed boundary in the conventional CFD. And I think the most commonly used immersed boundary for particle-laden flow is the direct forcing immersed boundary developed by Ehrman or modified from this. And this immersed boundary, because it's like it has essential 5 steps. Basically, you solve the Navier-Stokes equation without the body force, and then you interpolate the unforced velocity on the Eulerian grade. Basically, immersed boundary needs 2 sets of grade, one Eulerian grade for the fluid phase and the Lagrangian grade attached to the particle. And then you apply, you interpolate this unforced velocity to the Lagrangian grade. Then you calculate the body force based on the difference between this interpolated velocity and the desired velocity, which satisfies the no-strip condition. And then you distribute this F back to the Eulerian grade, and you correct the velocity at the Eulerian grade. And this one is very easy to implement when the geometry is complex, because you have a Lagrangian point attached to the solid body. And also, this interpolation only depends on the relative difference. It does not involve the geometry of this surface. And this diffusion, this boundary diffusion, introduce a lot of numerical diffusivity, then it have better robustness for moving boundary treatment. But the advantage of this immersed boundary is also quite obvious. First, it only first order accurate, and also it's require iteration to satisfy the rigorous no-strip boundary condition on the surface. And because it mixes everything up to this body force, so it is difficult to analyze. And the most important issue for us is that it cannot compute velocity gradient or like the dissipation rate correctly in this close to this particle surface. I think this is a big issue if we want to study the local disturber flow around the particles. And so you might have heard that in some papers, people claim that the immersed boundary has second order accuracy. But one scholar I respect a lot says that one mathematical proof worth more than 100 numerical simulations. So we can actually prove the immersed boundary only has first order accuracy by using a very simple problem. This is like a channel flow, a plane channel flow at the steady state. And the analytic solution looks like this. It's quite, you just integrate it twice and you get this. And for this problem, the immersed boundary method, this analytical problem can be also solved analytically. And by solving this, you directly see that the velocity gradient is, the error of velocity gradient is on the order of 1, and the error of the velocity is on the order of this delta, or like the gray spacing. And we have also conduct like very complex we have actually conduct a very complex systematic comparison between the IBB and IBM. For example, this 2D case of a free settling cylinder, this shows that the bounce back, the internal bounce back will have more severe force fluctuations, and these fluctuations are due to a numerical problem. Because the force in the Euler method applied to a moving particle problem, the force depends on the location of the solid object relative to mesh lines. But this is not physical. And the immersed boundary has a less force fluctuation, so it has a better robustness. And we also extend this comparison to directly to particle-laden turbulent flows. And this is for the overall, the decaying of the turbulent kinetic energy and dissipation rate look good for both methods. But if you look at the local profile, this immersed boundary will have some underestimated dissipation rate profile. This is not physical because from the Stokes solution, you will know that the dissipation rate will go like monotonically when it's approached to the particle surface. So these results makes us prefer to use the bounce back, interval bounce back based LBM for the particle-laden turbulence studies. Of course, there is another category in the LBM world for treating no-slip boundary method, which is called immersed moving boundary method. This basically design this additional collision operator to satisfy the boundary. And we can apply our analysis. We can prove that this is just equivalent of the immersed boundary, but it's realized in the mesoscopic LBM world. And it also only has first order accuracy. But because this directly in this scheme, it directly induced the porosity into the equation. So it will have some unique advantage when you apply this method to porous media flow, for example. And although we don't use the immersed boundary method for our particle-laden turbulent flow, we have done some improvements for the immersed boundary method. For example, like usually you need to have an iteration to enforce a precise no-slip boundary condition on the Lagrangian on the particle surface. But we can prove that in this ideal case, this iteration just like create a series of this boundary force, and the limit of this series will give you precise boundary, the no-slip boundary. And by realizing that, you can just amplify this force, boundary force, with a coefficient alpha, and the alpha has an analytical value 8/3 for 4-point delta and 2 for 3-point delta function. And this has also been found in other people's work, for example, Tao's work. And another thing, we also try to fix the dissipation rate calculation of the immersed boundary. And the previous solution is that because the velocity gradient outside the diffuse layer is correct, so you can have this 2-point and you do extrapolation to get the correct velocity gradient within the boundary layer. But this extrapolation, whenever you do, is only good when the distribution of this velocity gradient is linear or quasi-linear. For particle-laden flow, where this velocity gradient follow a Stokes solution, this extrapolation will not work. So because the boundary forcing changing the Navier-Stokes equation is a key issue. So we invent this like single-sided way, like we only apply the force, distribute the force to the solid region. We don't distribute the force, boundary force to the fluid region. This can correct the dissipation rate calculation. But the downside of this method is that the torque is no longer preserved when you do the interpolation, because you do it single-sidedly, and it will give you a more severe force fluctuation. So it's up to you to decide which feature is more important by choosing the correct numerical methods. And the last part, the second last part, I will show some progress of how we apply this method to particle-laden turbulent flows. And the first case is this decaying homogeneous isotropic turbulence. And this is the most, it is simplest form of turbulence. So we add particles in and we ask, because for single phase decaying homogeneous isotropic turbulence, people have realized that once the turbulence is fully developed, the decaying of this turbulent kinetic energy follows a power rule. Of course, it's debatable, but many people have already studied this problem. For example, you can see some big name here: Komgrove, Batchelor, Southman, Carson, right? So our question to ask is that once we have particle, first, will the decaying of the turbulent kinetic energy still follows a power rule? And how this, if it is, how would this end change? And we did a lot of simulations. We actually used our LBM code to generate over like 300 data points. And we confirmed that even you have particles, the decay of turbulent kinetic energy will more or less follow a power rule, power law, and the relationship between this particle-laden N and the single-phase N will determined by the mass loading and the density ratio. And this is the scaling law we developed to how to predict this N in the particle-laden world. Also, we apply this to forced homogeneous isentropic turbulence. And our question is that to what is the parameter dependency to determine like how particles will modify their property of the turbulent flow, especially in this case, what would the turbulent kinetic energy and dissipation rate change according to the particle parameters. And we use our simulation method to generate the data, and we generate these scaling laws. And but these scaling laws are kind of empirical, and this only represent the first step to model this problem. Recently, we collaborated with Professor Balachanda at the University of Florida, and we try to develop a more mechanistic and a more general prediction or scaling law for how do you predict the turbulent kinetic energy when you have particles. And this scaling law. Okay, so I need to speed up a little bit. And this scaling law match with most of the DNS and the experiments data. Of course, this also is very preliminary. There's a lot of improvements it can be done. For example, if the turbulent flow is inhomogeneous, how do you modify this scaling law? And we also were also interested in how how the turbulence will affect the particle, for example, particle drag. And if it's laminar environment, many of you know this Schiller-Newman correlation to predict the particle drag. But if it's in the turbulent environment, how would this CD change? And this problem had been studied for many years, back to 1980s. And I just show a summation from Crow's book on this problem. And nowadays, with the DNS fully resolved numeric simulations, we can do it numerically instead of measuring it experimentally. These numerical simulations can provide more details, and we generate this scaling law of how this drag force will change. This was first done by Holman, and we further consider about the homogeneity in this turbulence. Like we put another coefficient here. And recently, I applied this to like how the turbulence affected the settling speed of the particles. This animation shows you the particle trajectories in under different like turbulent intensity and the density ratio. And in all the case, we found that the turbulence will reduce the particle settling speed. This is consistent with some other previous studies by the Luca Brandt's group. And also we extend this to homogeneous shear turbulence. This is the simplest form of the shear turbulence. It's a sustainable turbulence because you have shear, you have production of turbulent kinetic energy, but it's still homogeneous. And the most important part here is how do you implement the shear periodic boundary or the least Edwards boundary with finite particles, and we figure out algorithms to implement it, and we successfully done this simulation. Of course, we can use this code to do more deep physical analysis. And as you can see here, by adding particles, basically it breaks the large scale vortices and create a lot of small vortices. Because small vortices are more isotropic, so you can expect that the isotropy of the turbulent kinetic energy distribution will be enhanced by the presence of particles. And also in this case, because the particles do not follow the flow, so it will like disturb the flow and enhance the Reynolds stress, which essentially enhance the turbulence itself. And finally, we apply to like wall-bounded turbulence, for example, the particle-laden channel flow and pipe flow. And we use by the method of volume average, we can derive the turbulent budget, the kinetic energy budget equation for the two-phase flow, and we can use our data to like examine every term in this budget equation, and we find out that like particles have enhanced some mechanisms and reduced, suppressed some mechanism, and even create some new paths for the turbulent kinetic energy motion. So this gives us a better understanding of how particles modify the turbulence. And finally, this is the final case. We recently did some work to like try to find an explanation, because this near wall turbulence is dominated by this quasi-streamwise vortices, and under this quasi-streamwise vortices, particle will find its preferential locations to locate. Previously, like people will find that the particles will preferentially like locate in the low speed regions, but some other case will find it will locate in the high speed regions. And for the later case, the mechanisms has not been clear, very clear. So we did very careful simulations to seek for a reason for this, and we realized that the reason for the particles to accumulate in the high speed streaks is because once these particles enter the near wall region, they will be ejected away from this. So it's basically a high speed region in, high speed region out. So there is no chance for them to move to the low speed region. But if you have sediment particles, then the particles will stay longer in the near wall region, and it finally will be swiped to the low speed regions. And we use this to review this mechanism. And finally, some a brief summary. First, there is no universally good numerical methods. So if LBM is not a good method for your problem, don't criticize LBM. You just choose another method, which is more suitable for your problem. But for our problem, which is particle-laden turbulent flow, we think LBM is a very suitable method because of the features we introduced before. And we developed interval bounce back based LBM to conduct fully resolved simulation for particle-laden turbulent flows. I think this is quite unique because most of the groups in the world, they use immersed boundary based LBM. And the accuracy, numerical stability of the computational efficiency of our method have been carefully validated. And comparing to the alternative method, this method preserves the second order accuracy in boundary treatment and ensures the correct local dissipation rate computation, which is important for our applications. And we have successfully applied this method to study different kinds of particle-laden turbulent flows, for example, homogeneous isentropic turbulence, wall-bounded turbulence, homogeneous shear turbulence, and it provides deeper ways to understand the particle-turbulent interactions. Of course, there are still many open questions to be answered, particularly how could we use the data generated from our fully resolved simulations and to do the modeling for the more industrial problems. Of course, a lot of our colleagues have already realized this problem, and they have already have paper published. For example, I've seen like Balachanda, Yu they have a lot of paper published. So if you are also interested, you can look at their works. So that's all my work. I'm ready to take questions.
Okay, it's a great talk. I think Dr. Ng gave a very nice overview of all the issues both with methods for particle flow. This brought a lot of memory to me in working with him. So please, you have a question, please write the chat window or ask, write in chat window or let us know one question. Or raise your hand. Okay, I see one already. Let me question. What do you think are the difficulties using OBM to compute particle with high rate of turbulence compared to low rate of laminar flow, and how many computational resources are needed to compute the flow field?
Okay, so of course you need a better grid resolution, because for our case we're doing like fully resolved DNS, so you have to resolve the like homograph lengths. This is like and also of course if the particle Reynolds number is high enough, then if you are not using a sufficient grid, the code will not be stable. For example, I give you a very this as I said, this is a very amazing. Of course, not done by me, but I get a lot of inspiration from their work. This is a very high Reynolds number flow, and to do this with reasonable computational resources, they have to do a lot of great refinement locally. If I remember it correctly, it has they have refined their mesh like over like 2 to the 12 orders. So basically, the finest grade and the most cost grade, the grid spacing has like over 1,000 times difference. So this is the difficulty. And if you talk about computational resources for our particle latent turbulent flow, we usually need the computational grid is like say, for example, for this case, we use like 512 cube, which is like 0.1 billion grid node. And of course, for LBM, this is more expensive because at the one grid you have like 27 27 distribution functions to store. So you need a lot of memories to do this. Of course, I mean, if you can apply some techniques, for example, adaptive grid refinement, then you can reduce the computational like resources. So this is very expensive, I would say, but as long as your code has been optimized, it can be relatively quick. As you can see, like although we are solving more equations, these comparisons show that our overall computation speed is comparable to the conventional methods. So I hope I answered your questions.
Okay, thank you. Let me ask one quick question. How would you compare particle resolved simulation with point particle simulation in the previous point particle simulation? What are the main advantages of particle resolved simulation? What more information can you get?
Well, the point particle simulation, first you get this you get the particle, the force, hydrodynamic force acting on the particle based on the equation. And I don't think this equation is accurate sufficiently, especially like when people do point particle simulation, they will like ignore a lot of terms, like for example, Bessel history force, added mass force. They will keep their only maybe this form. So in terms of particle dynamics, fully resolved method, directly calculating the force acting on the particle will be more accurate. Another thing is that if you talk about the particles effect on the turbulence, for point particle simulation, you don't resolve the disturbed flow. For example, usually you just add a feedback force, like you do the interpolations to the grid point, and this is not physical. I think. I mean, numerically, it may be good, but it's not physical. But in the fully resolved method, you can directly see like the disturbed flow is rigorously simulated. It satisfies the Navier-Stokes equation. So I think these are two aspects. Of course, like some people, I know there's only one paper in my mind done by Pedro Costa from TU Delft, I think. They did they directly used fully resolved DNS for point particle, meaning the particle size is much smaller than the cosmograph length. And they found that in terms of particle concentration, local concentration, if you include the Softman lift inside, then the point particle simulation is okay. But nowadays, I think it's still too expensive, at least for me, to do this kind of direct bridging the point particle simulation and the fully resolved simulation.
Okay, thank you very much. I think our time is up. On the chat window, I put down Dr. Peng's email address. So any of you have questions, you can send him email.
Yeah, please send me emails if you have more comments on my.
Or read his papers. Yeah. He has published quite a bit of papers over the years, over the past 8 years or so. Okay, thank you all for listening to this seminar. I think this is a wonderful seminar, wonderful exchange. So thank you all. Bye for now.
Thank you. Okay, I will end the sharing here.
Thank you, Professor Peng. Professor
So can I
Wang.
leave? Like,
yes.
Okay. Okay. 拜拜。
可以结束了，拜拜。感谢两位老师支持。
好，非常好，谢谢。